So today's topic is about experimental user study, and it's about designing experiments and how to organize your experiment, how to design your dependent variables, and how to design your tasks, and how to run the study, and how to prepare it, and afterwards how to collect the results and analyze them. So today we'll be talking mostly about the general stuff about how to design your user study. And in the next lecture, we'll talk a little bit more about statistical tools or statistics that you can use to analyze the results. So far we've been talking about different research methods in HCI research. So there are other research methods such as measuring system performance and sort of things, but we were focusing about the user study, having your users in your study and collecting feedback from them to improve or validate your user interface design you've had. And for that, we've briefly touched or briefly covered various different styles of user study, like observing people or interviewing people, doing some survey using questionnaires, and so forth. And we also talked about the usability testing last time, like recruiting participants and letting them use your interface and counting the number of errors they make, how fast they can do the task, and so forth, to make sure your interface is usable. And then today we're going to talk about the user experiment side, which is more focused on academic research, while the usability testing is done in industry as well to make sure their product is usable. But user experiment is more focusing on the academic aspect of developing new knowledge and new finding of knowledge and so forth, and validating those. So among the different type of user studies, the user experiment alone is for experimental investigation, while the other methods are more focusing on descriptive or explorative investigation. I think if you recall the very first lecture we had in this track, descriptive or explorative investigation is more about understanding and knowing the features or features of your design interface, how fast people can use, how easy it is enough. So it's all about the interface you're investigating, the one interface that you're investigating about. Experimental investigation is more about comparing your interface with others, like the state of the art or the standard that people are already using, and comparing those two to make sure or in some way kind of demonstrate that your new idea or your new interface is better than the state of the art. Okay, so proving that based on the experiment. So again, user experiment is a method of academic research in HCI. So if you are trying to publish your work in an academic venue, such as your thesis or your paper to a academic journal or a conference, then definitely what they will expect from your publication is if you did a user experiment to prove or show that your idea is validated or so. And the user experiment is always hypothesis driven, which is a specific form of your research question that can be, that compares basically multiple conditions. At the minimum, your own interface and the state of the art, what people are already using. And based on that is to discover the causal relationship between the independent variable and the dependent variable. By independent variable, in most of the cases in HCI field, will be the type of interface the user is using. And the dependent variable could be like how fast they can do certain tasks or how less error they can make, and sort of things. And comparing those multiple conditions, your own design of your interface and the traditional interface, and showing that your new design results in or causes a better user performance or better user experience or better usability and so forth. So it's all about comparing multiple conditions and discovering that one of the conditions, which will be your own design, makes difference to the usability or user performance side of the measures. And another important aspect of a user experiment is it should be replicable, which means if someone reads your paper and does the same experiment, it should come up with the same result, right? So otherwise, it cannot be generalized what you found from your experiment. So for example, if you design a new type of keyboard and then you compare it with what we have today with QWERTY, and then you claim that through a user experiment you found your new layout of keyboard was made people type faster, then if you publish that in a paper, then if someone did the same experiment and if they found it was not really faster, then there's no point, right? So it should be replicable so that others can also try it and find they have the same results. So at least, so the minimum is the replicability of the experiment. So you should be clear how you did or how you conducted your experiment and what kind of tasks they did and what kind of measures you used to make clear those so that another researcher could run the experiment again and see if the outcome is consistent or not. And then once you've run the experiment, so the user experiment always involves some kind of statistical test of your hypothesis. So if your hypothesis was with this new keyboard, people can type faster, then it's, and based on your results from the experiment, you should be able to say how likely is to either support or reject your hypothesis so that you can make conclusion that your hypothesis was correct or not in essence. So again, to explain a little bit more about what how user experiment is different from usability testing we've learned before. Like usability testing also was about recruiting participants and letting them use your interface and measuring some user performance or usability ratings and so forth. So the main difference is the methods can be the same. It could be using, again, the same observation or key logging, measuring task performance using task completion time or number of errors. Those kind of methods that you use to collect feedbacks could be the same, but the goals are very different. So the goal of the usability testing is to identify usability problems and issues of the product. So if you designed your new keyboard layout, if you're running a usability testing, the purpose of the usability testing is to identify the problems or the performance people have with your that specific interface, and based on that to improve your design or in the next iteration. But the user experiment the purpose of the user experiment is to answer research questions or discover new knowledge in an essence. So user experiment is more as an academic research method. So it's not only about you have your new interface, and with this interface, people had this kind of problems or this kind of good aspects of usability, but it's more about if this really makes difference from the state of the art or what people are already using. So the user experiment is all about justifying or making clear that your new idea is better than what people already know about. So that's the main difference. But the method itself, like recruiting participants and letting them use the interface and then measuring their performance or usability ratings, and those kind of things will be the same. But the main difference is either you are testing only your interface or are you testing it with another interface so that you can compare with the state of the art or the already known knowledge and prove that your new finding or your new interface is making difference to the field of the study. So this table kind of shows a little bit more detail. So usability testing is all about improving products. So if you have your new product, if you run a usability test, the focus is around to find the problem of your product and fix them. But the experimental study is about discovering new knowledge and making difference in terms of academic knowledge out in the field. Usability testing usually can end up with fewer participants. Remember the Nielsen rule where 5 participants mostly recognizes 80% of the problem of your study, right? So if you're doing the usability testing to find problems of your interface and fix them, usually you won't need more than 10 or so participants because most of the problems of your product or your interface will be identified by 5 or less people. But if you're running an experimental study, you will have to do a statistical test between different conditions, and you will have to have a kind of a probability value that says your interface is better than the other with certain amount of percentage. So to do those kind of testings, you will definitely need more participants, like some number around 15 or 20 at least, depending on your study design. But anyway, in general, with usability testing, you can have lesser people to identify the problems of your product. But for experimental study, you will need more people because basically it's about statistics and how likely it is different from other conditions. And the purpose of the usability testing the result of the usability testing to inform the design, which means the findings from your usability testing will be used for improving your design. So if you found like 7 problems of your keyboard layout, then you will be fixing them based on that. But hey Joshua, but the purpose of the experimental study will be not only improving your study, but to draw statistical results that you can prove or show that your idea is better than what people are already using. Okay, and usability testing usually not completely replicable because the usability testing itself is about your prototype. So later on, your prototype might not become valid or might not become available. So it's not focusing about the replicability because you're focusing on the special case. But the user experiment, since you are trying to generalize your finding, the study itself should be replicable. And with the usability testing, the conditions are controlled as much as possible, but you can be flexible. Like if you found some problem, if one of the keys were not working well with your usability testing, and if you found maybe a different layout may work better, then you can make those changes on the fly and continue doing the usability testing. But with the user experiment, you'll have to have more strongly controlled situations. So if you had some people already running your experiment, and if you found that you might have to change some of the settings, then you'll have to throw away the previous results and rerun the study with the new settings and so forth. So it requires more strongly controlled conditions. And in an essence, the results of your usability testing is a feedback to improve your design, but the outcome of the experimental study is to mainly become a scientific report or paper or thesis that kind of shows the new idea or your new knowledge that you've discovered to be propagated to the other scientific community. So again, the methods you use might be quite similar, but the focus or the purpose of the study, the two studies, is quite different. So that's the main thing. And the main difference would be that's in an essence or from the perspective of who is running the study, the main difference will be, are you having at least two different conditions and comparing them, or are you just trying to test one specific interface by itself? So this is a typical procedure of both usability testing and the user experiment. If you recall, when we were talking about the usability testing, it's quite similar. The procedure is quite similar, but the main difference is in the middle here. So you set the goal of the study, and then you let your users or your participants user experience your solution or your interface, try doing specific tasks, and then collect qualitative feedbacks, and then analyze them and answer the research question. The main difference is here, where the usability testing didn't require multiple conditions, but the user experiment has to have multiple conditions. And that condition itself is in some way called independent variable. And collected feedback is called dependent variable. So in essence, the difference between the usability testing and the user experiment is either you have multiple conditions or not. Okay. So when you write up your thesis, if you run a user study that has only one condition, then you cannot really say it was an experiment. You can say it was a user study or usability testing, but you cannot say it was a user experiment if you didn't have two conditions that you compared different settings. So how to run a user experiment? There are certain steps. So as other user studies, user experiment also starts with establishing your research question. And for the user experiment, they require or prefer a specific type of research question, which is very specific. And they are called hypotheses. And basically what hypothesis is a sentence that kind of summarizes what the prediction summarizes the prediction of the outcome of your study. So for example, if you again came up with a new layout of keyboard, and if you're comparing with the current keyboard layout, what people are widely using, the QWERTY keyboard, then the prediction of your study, what would you expect from the outcome of the study? So maybe, yeah, types better, essentially. So the hypothesis could be something like my new keyboard layout. When people type with my new keyboard layout, they will type faster than the QWERTY keyboard or something. So it's basically a prediction of what the outcome of the study will be. And it should describe something about the relationship between the independent variable and the dependent variable. And independent variable is most of the time the type of interface they use. So again, like as in the example, when the users will use my new layout compared to the QWERTY keyboard, it's including the two conditions, right? So it's including the independent variable, and the dependent variable would be how fast they can type, right? The fastness or the test completion time is the dependent variable. So the hypothesis should include those kind of components in it. And then once you have that hypothesis defined, then you run a specific procedure of the experiment, and of course you'll have to design the procedure and run the procedure where participants experience different conditions, one with the new keyboard and one with the traditional keyboard. And then they will do a certain task, such as you can give a predefined page of book and then let them type, or whatever kind of sentence you can give them and then let them type and measure the time they are typing. And you measure the records, and that's the dependent variable. And once you've collected those measurements, then you answer the research question by analyzing the results using statistical analysis and showing that indeed the time they took with your new keyboard took less time than the traditional keyboard. And then by doing that statistical analysis, you are testing your hypothesis, whether it was true or false, based on the statistical analysis. So a little bit more details about each component in your user experiment design. So independent variable is basically a variable that is independent of the participant behavior. So using different keyboards, whatever they do, it's independent from the participant behavior. They cannot change the keyboard layout, right? So it's given to them. And it's basically a possible cause of the change in the independent variable. So the independent variable is defined by the experimenter yourselves, and it couldn't be changed by the participants, but it kind of is kind of expected to change the outcome, or such as the test completion time or number of errors they make and so forth. So it's in that sense, it's a cause part of the whole hypothesis. And usually these are the factors that the researchers are interested in studying. Of course, your new keyboard design is what you are interested in to show that it's better than the others. And sometimes it's also it's basically defining the conditions of your user experiment. And the dependent variable is basically the outcome or effect of the researchers that are interested in. So example, the outcome is typing speed, like how fast they can type. And it's called dependent because it depends on the participant's performance, right? So what participant does kind of decides what the time or the number of errors they make. So it's dependent to the participant's behavior. And it's usually the outcomes that you need to measure, such as test completion time or number of errors they made and sort of things. So those are basically independent and dependent variables. But sometimes you get confused with the independent variable and the conditions. And this kind of table here kind of shows how the independent variable is different from the conditions. So let's say, so in an essence, conditions are factorized levels in all independent variables. And what it's calling, what it's saying is, before we go with this example, maybe we can do with the keyboard example. So type of keyboard is an independent variable, and the conditions are the new interface, the new keyboard layout you invented, and the QWERTY keyboard that other people are widely using. So even if number of independent variable here is 1, and the conditions are 2. Okay, so independent variable is kind of a one factor that kind of covers the whole conditions. Like like for example, if you were comparing your new keyboard and the QWERTY keyboard, and remember there was another kind of keyboard called Dvorak. So if you were comparing 3 keyboards, then still the independent variable is type of keyboard layout, but there are 3 conditions you're comparing, right? And coming back to this slide, if you're comparing, and sometimes you can have more than one independent variable, like for instance, if you're trying to compare different pointing interfaces, like say you invented Kinect by yourself, and you wanted to show that it's better than other gaming interfaces like Wii and Move. And so the type of pointing interface you're using is one independent variable you can compare between. But somehow you came up with an idea, maybe my interface is good for pointing at close objects, but maybe not good for far away objects. Maybe other interface might be better with far objects, and mine will be better for close objects. Then you can come up with another variable, which is the target is far away or close. So you can put another independent variable here. How far is the target? And then now you have two independent variables, but the number of conditions you have here is actually the combination of two, right? So you end up with 6. So if you had 3 conditions for independent variable 1, which is type of interface, and if you had 2 conditions for independent variable 2, which is how far is the target is, and then you end up with the conditions, which is 3 times 2, which is 6 different conditions that you have to test and compare to make a conclusion that your interface is better in close targets, but not with the far target, and so forth. So again, in an essence, you can have more than one independent variable, and you can have more than more than 2 conditions within each of the independent variables. And in your user experiment, you'll end up with having all factorized combinations of conditions in all of the independent variables. So in some sense, if you have too many independent variables, then you'll have too many conditions that you have to ask participants to try on, and that will kind of take a lot of time to let them try out and so forth. And the number of conditions for each independent variable, sometimes they call it levels in that independent variable. So for instance, in this axis here, this column-wise, it's showing the independent variable of type of interface using, but the levels of that independent variable has 3 levels, and it's either we connect or move. And in this case, there is 2 levels in this independent variable of the distance to the target, and so sometimes they call that levels. So typical examples of independent variables, obviously it's type of interface is one of the typical independent variables that you most of the time want to include, since your study will be around your new interface design and you want to compare it with how people deal with the traditional method. So sometimes you can also include independent variables, those are related to the user, such as age or gender, or their cultural background. So sometimes you want to show, like as was in this example, not only the interface, depending on the interface or the target, maybe you can compare between male and female, or more novice users and the experienced users, and compare maybe my interface is good for novice users, but maybe not for experts. But in the other way around, my interface could be targeting for experts, so that the experts might feel better, but maybe it could be harder for novice. So you can have your independent variable with those kind of demographic information or the background of the participants. So those are the typical examples of independent variables. Typical examples of dependent variables are basically the measurements you measure, how fast they can do the task, or how easy it is to use, and so forth. And we talked quite a lot about this when we were talking about the questionnaires and 4 different measures we talked last time about. And so it could be test completion time or speed. Could be something around accuracy, such as how many errors they make, or could be subjective satisfaction, such as a questionnaire you ask with Likert scale rating and so forth. Could be how easy is it to learn, or how they can recall what they learned last time, if it was all about how easy it is your interface to learn. Or it could be also about physical or cognitive demand or load, and how tiring it is to use, or how much fatigue or how much stress it gives while you're using. And I think when we were talking about questionnaires, we briefly talked about NASA TLX, which is a questionnaire specifically designed to measure this kind of stressfulness of your using your interface. So those are typical examples of dependent variable. And there are also other terms in experimental design, which is one controlled one of them is controlled variables, and it's something about you are not much interested in, but you'll have to make it controlled or consistent. So for example, if you're again running an experiment comparing your new keyboard layout, comparing with QWERTY keyboard, and you are doing it in this room, and during the daytime, if there was quite a big noise because of the construction outside, and some of the participant was doing it while it was quite quiet, and if some of the participants was doing it if it was quite noisy, then maybe that noise might have affected some of the participants, and the result might come out differently. So you'll have to control certain variables such as noise levels, even though you're not interested in how people type faster when it's noisy or less noisy and so forth. So it's not a topic of interest of your study, but should be controlled in a certain level. You might either make it always noisy, or you might have to make it always quiet enough so that it doesn't affect your results. So those kind of variables are called control variables that you have to think of. And the other, those you cannot really control are basically random variables. So for instance, how much tired they feel you might not be able to really control it. So of course, so again, either a variable becomes a controlled or random is basically your choice. So you can either control them or leave it as a random factor. So you don't really care about it. And also, like for instance, the gender could be also even a non-controlled variable. So it could be a random thing. So you don't really care about comparing the performance between male and female, but you can just leave it as a random variable. But the important thing here is that when you leave those variables as random, then you'll have to randomize the assignment. We'll talk about this later. Maybe might not make sense for you talking about the random assignment. So, but anyway, for now, just remember that the other variables that you are not interested in comparing, you might have to either control it or leave it random. But you'll have to make decisions how you are going to deal with it and report it in your thesis, that which variables you controlled and which variables you didn't really control because you thought it won't affect that much. And sometimes there are also confounding variable, which is basically extraneous variable that's correlated both with independent variable and dependent variable. Those who were in the last lecture remember the example of stork and a baby. Like if you were doing trying to make a conclusion between if there is a stork, then there is a baby that was somehow related, but it doesn't make logical conclusion, right? And we had another variable, which is the heat, the warmness of the chimney, which kind of explains why there is highly likely a baby when there's a stork on a house. So those kind of third variable that kind of relates with the other two that could affect the results are called confounding variables, and so forth. But so those are kind of variables, type of variables that is involved in running a user experiment. And as we've talked about earlier, user experiment is all about testing hypothesis. So making a hypothesis, and then through an experiment you either prove or deny your hypothesis through the experiment. So in essence, user experiments is all about testing the hypothesis. And hypothesis is a precise problem statement that can be directly tested through an empirical investigation. So if your hypothesis cannot be tested, either if you cannot really say if it's true or false, then it you'll have to rethink the wording of your hypothesis and revise it so that you can make sure that it could be either falsified or supported with your experiment. And compared to a theory or general research questions you have been dealing with so far, it's more a smaller or focused statement. So usually it's just in a one sentence and can be examined or validated using a single experiment. And should be clearly defined so that it could be either proved or disproved using your experiment, and should have an appropriate scope. So it shouldn't, again, in one sentence you cannot really put a lot of things, but you can, your scope should be really focused on either focusing on task performance, or is your focus on how easy it is to use, or and so forth. So sometimes in a user experiment you can have more than one hypothesis. So, and you can also even break down into multiple hypotheses. So like for example with the keyword, you can have a high-level hypothesis saying depending on the type of keyword user is using, they might have a better user experience as a high-level hypothesis. And then you can break it down into, like, using my keyboard layout, people will type faster than using QWERTY. That might be one hypothesis, focusing on how fast they can type. Another one could be people might be more satisfied using my keyboard, or feel easy using my keyboard. Those kind of different measurements could be break down into different hypotheses. And inside your hypothesis, you should include independent and dependent variable clearly, so that you can, which is basically making it easier to either prove or disprove using your experimental results. So one example here is for a pointing test, there is a significant difference in mean test completion time between the Wii and Kinect, is one of the examples, which is, so it's defining what kind of task it's using, and then it's talking about there is a difference between the conditions with test completion time, which is dependent variable, and between Wii and Kinect, this is showing what's the independent variable and what are the conditions in there. And another example could be Wii will show less error compared to Kinect when doing a pointing task. So again, here it includes different conditions, which is independent variable. Less error is the dependent variable, and saying doing pointing test shows what the context is about when you are measuring this error. So once you have your hypothesis, as we've talked earlier, doing an experiment is all about either proving or disproving your hypothesis. And in an empirical way, it's harder to prove a certain hypothesis than to disprove it. Why is it? Can you think of why? Yeah. So only one example. So by empirical study, if you find something that can disprove something, it's only one example is enough. But if you want to prove certain things by empirical way, you'll have to check every instance, right? So if you want to prove the sun always rises from the east, then you'll have to prove every day, right? Every day, and even in the future, you have to prove maybe some time in the future, maybe some kind of strange thing in the universe will happen, and the Earth will start revolving the other way around. So you cannot really prove that the sun will always rise from the east, but if you find a certain instance that one of the day in the history it rose from the west side, then you can certainly disprove that statement, right? So it's easier to disprove something than prove something in an empirical way. So this proof is relatively easier, and that's how research scientists deals with the experiments. So they don't try to prove something, but they try to disprove something, which is easier. So they came up with an idea of null and alternative hypothesis. So if you want to show that your keyboard, with your keyboard layout, people can type faster, if that's what you want to show people, it's harder to prove that by showing every time you do this, it's always people type faster with your keyboard. It's hard to prove it by an empirical way, but it's easier to disprove it. So people came up with a concept of null and alternative hypothesis. So what you want to really say, you put it as an alternative hypothesis, and then you negate it, saying there is no difference between the two keyboard layouts. So people are not really faster than when using my keyboard layout. And through the experiment, you prove that this null hypothesis is false, so that you can kind of supporting the alternative hypothesis, what you really want to say. So once you have your hypothesis that you want to support, which is your keyboard layout is faster than the other keyboard layout, then you'll have to come up with a null hypothesis, which is an opposite of it, saying that there is no difference between your keyboard layout and conventional or traditional keyboard layout. And through the experiment, what you do is you disprove your null hypothesis so that you can support the alternative hypothesis, which is actually what you want to really show or present. Okay? So is it clear enough what null hypothesis and alternative hypothesis? So basically what you want to show to others is this alternative hypothesis, and null hypothesis is an opposite of it, which you want to disprove it through your experiment so that you can support or support with your conclusions. So it's a little bit complicated, but this is all about what scientists came up with. It's always hard to prove something, but it's easier to disprove something. So why don't we disprove what we don't want to support so that we can kind of support what we really want to prove. So it's becoming a little bit complicated, but hopefully that makes sense for you. Are we all good with this? Okay. So for example, if you invented, again, Kinect, and you wanted to show that Kinect is better than the other gaming interfaces, then all you want to say is this alternative hypothesis, right? So there is a difference in task completion time between the three. And then, since it's hard to prove this in an empirical way, you negate it. You take an opposite statement saying there is no difference in task completion time between the three conditions. And then through the experiment, what you are trying to do is falsify or disprove this null hypothesis so that you can make a conclusion that since this is not true, maybe H1 is more likely. So the goal of the experiment is, again, to find statistical evidence. So by disproving or proving something, what we all do, what the scientists do or researchers do is run a statistical test and come up with a probability of how likely is this statement true or false. So it always involves a statistical evidence, which is basically a probability of either this statement being true or false. And again, statistics cannot really prove or disprove because it's all about a chance. So even if you have a 95% of chance of this statement being true, there is still 5% of chance that it could be false, right? So since the tool we are using to prove or support the hypothesis is a statistical tool, and it's all about probability, we cannot really say that it was fully proven or fully disproven, but what we can say is there is a high chance that we can support this, or there is a low chance that we cannot can support this or so. So the purpose is to prove or disprove, but since the tool we have is the statistical tool that ends up with a probability, the word we have to, all we can say is either we can strongly support or accept this statement, or reject or do away with a certain statement. So it's kind of a small thing. I mean, kind of could feel like a nitpicking thing, but it's sometimes when you write up a thesis or a paper, some reviewer will say that this is just one study and it's about statistics, so you cannot really prove or disprove something. So someone might comment about this. So you will definitely have to be careful of choosing the words when you write your report. So again, try to use the word you can reject or accept or support certain hypotheses, but try to avoid using "I proved this hypothesis is true or false." So, and since we are using statistics to see if your hypothesis is more likely or less likely to be supported or falsified, statistics is all about sampling. So, and user experiment is all about sampling as well. So you are trying to sample certain participants and make a conclusion of maybe most of the users will do the same thing. And if you are doing statistics, you are kind of sampling a certain people. So let's say all of these dots are the users out in the field. And when you're running an experiment, you just sample certain people, right? And then you run the experiment. And if you made a conclusion with these people here, it might be likely that in, let's say, red dot is there was no difference between your new keyboard and the old keyboard. But let's say if your sampling was like this, and if your conclusion was there was a difference between the two, then there is still a chance that there could be the results you had in your experiment might not be true in a general sense. So you should be aware of that the conclusion you had in your experiment is not kind of the truth that's written in the stone, but it's just a single finding of your experiment. So you'll have to be careful of that. So thinking of that sampling error that you can make, you can think of different type of errors you can make. So let's say you ran your experiment and you ended up rejecting your null hypothesis. You can make a conclusion either rejecting your hypothesis or you're retaining your hypothesis, right? But in the real world, where in this picture, well, in the real world with the whole population, it could be actually H0 or the null hypothesis is true, and H1 is false. So this axis kind of shows what is in the reality with the whole population, and this axis is what kind of decisions you made throughout your experiment. And if you rejected H0, and in reality, if it was H0 was true, then you're making an error of false positive, making a false claim of rejecting the H0. And that's called type 1 error. And if you retained H0, and if H0 was truth in the real world, then you made the correct decision, right? Your finding was correct. And if H1 was the truth in the reality, and if your study results came out with rejecting H0, then that's again the correct decision, right? Since H1 and H0 is opposite. But if the reality was H1 and your study ended up retaining H0, then you're making type 2 error, which is a false negative of saying there's no difference, even if there was indeed a difference in the whole population. So, and in scientific community, people are more careful or more preservative, how to say, more conservative about making false claim of new finding. So scientists are more considered or worried about making this type 1 type of error. So, which is saying that your new idea is better than the traditional thing, while in fact there is no difference between the two. So it's a little bit complicated. Does it make sense? So let's say H0 is there is no difference between your new keyboard and the traditional keyboard. And if your study kind of found that your keyboard is better than the traditional keyboard, and if it in the real world with the whole population it was not true, then that's the error that scientists are trying to avoid. And the probability of making type 1 error is called alpha, and probability of making type 2 error is called beta. So throughout your experiment, what we are trying to do is making this probability of making this error lesser as much as possible, so that you can claim that the conclusion you made of rejecting H0 is not really, it's concluding that making a conclusion of rejecting H0 while the H0 is the truth is less likely, so that you can claim that your conclusion is I mean, there is a less chance of making false conclusions in your study. In some way, alpha and beta are interrelated, but the experimental researchers generally believe type 1 errors are worse than type 2 errors because they are very conservative about they are trying to make sure that the new idea you came up with is trying to make sure that is really making a difference, while they don't want to see some false conclusions that saying the new interface design is better than the traditional thing, while in fact there is no difference between the two. So scientists try to make the alpha level very low, like less than 5%, or in some conservative cases less than 1%. Of making this kind of type 1 errors. So when you are testing your hypothesis, let's say H0 is no effect of the solution, which is making H0 is no difference between the new keyboard and the older keyboard. And the p-value is the probability value of assuming that H0 is true, which means there is no difference. The probability or likelihood of observing the effect, which is rejecting the H0 and saying that the new keyboard is better than the older one. So usually when you run a statistical test, it will print out a probability value, which is in short p-value. And this p-value, what it's saying is the probability of making false conclusion of your interface is better than the other, while in fact there is no difference between the two. So if the p-value is low, then that means it's very likely that saying there is a difference between the conditions is very likely, and it's a lower chance that that you're making false positive about your study. And so that's all about probability. And there is another concept called alpha level. So since this probability value could be anything between 0 and 1, and some people can think probability of 10 is really low, 10% is really low, or some people can think 10% is still high, so some people can think 5% should be lower, or so. So there should be a certain threshold or certain reference, and the alpha level is that reference value that you compare your p-value with. And in most of the cases in HCI research, people take this reference value as 0.05, which is 5%. And if it's less than 5%, then people usually say it's a significant result, which means the results you've got has a very low chance of being making type 1 error. So it's all about either the p-value you get through the statistical result is either lower than alpha or higher than alpha. So you cannot really say, even if you have a p-value printed out from your statistical tool, if it's 0.0000001, then you cannot really say it is more significant than p-value of 0.04. It's either significant or not. It's not about if it's more significant or less significant. It's kind of binary thing if it's higher or lesser than the alpha level. So let's go with an example. So let's say we compared V and Kinect, and we wanted to say that Kinect is faster than V. And then since that's what we want to show, we will have to make an opposite statement for the null hypothesis, saying between the V and Kinect there was no difference between mean test completion time. So that's the null hypothesis. And through the experiment, we were trying to disprove this or reject this. And once we tested, we observed we took like in average 100 milliseconds to completing the task. Kinect took 500 milliseconds completing the task, and there is a 400 millisecond difference. And you run a statistical test, and the probability of this difference being meaningful was printed out 0.04. And this probability value is the probability of rejecting H0, while H0 is actually the truth, which means making false conclusion of rejecting H0. So since the probability is very low, which is below 0.05, which is commonly accepted level of alpha, so that we can make a conclusion that since the probability of making falsely rejecting H0 is very low, then we can actually reject H0. And rejecting H0 means H1 is more likely the truth. So by rejecting H0, which is there is no difference between the two conditions, then we support the alternative hypothesis, which is there is a difference between the V and the Kinect, and the difference is 400 milliseconds. So are we all on the same page with how this all works? So it's kind of complicated, kind of negating the hypothesis and so forth, but it's trying to make sure this is all about trying to make sure we're not making any false conclusions out of it. So trying to make the probability of making false conclusion as much as possible, as less as possible, I mean. So again, to recap, if you want to prove something, such as your interface is better than the traditional way, you first make a null hypothesis, which is a negation of it, which is basically there is no difference between your interface and the traditional method. And through the experiment, you collect the measurements and run a statistical test. And the statistical test, what it prints out is the probability of rejecting the null hypothesis, while in fact the null hypothesis is the truth. So the probability, if it's lower than 0.05, which is commonly accepted alpha level, then if it's lower than 0.05, then what you can say is there's a very low chance of making false rejection of H0. So we can actually reject the H0. without worrying about making false rejection. And by rejecting H0, we are supporting the opposite, which is H1, what we really want to say, that our new interface is better than the traditional one. Okay, so in essence, create your hypothesis, make a null hypothesis, run your study, run the statistics. It will print out the p-value. If p-value is less than 0.05, then you're happy because you can reject the H0 and you can support H1, which is you really want to say. So, and in statistics, there is a term called significant difference between the two, significance or level. Like the p-value is sometimes called significance level. So many of the statistical tools kind of compare two conditions and see if the mean value of the two is different or not. And when you're saying there was a significant difference, that means p-value is less than certain threshold, which is usually 0.05. And if p-value is higher or same or greater than 0.05, then you say there was no significant result or there was no significant difference between the two conditions. So, and even if you found a significant difference between the two conditions, you'll still have to be careful with effect size or amount of difference between the two. Remember, if you go back to this slide, we ran the statistical test and the p-value was less than 0.05. So we can say there was certainly a difference between the two conditions. But if the difference was 400 milliseconds, is that meaningful or not? That could be depending on the context or the task you were doing. So let's say if this was all about the brake, designing a new interface for stepping on your brake, like if you wanted to change your braking mechanism to grabbing or pressing a button on a car, then maybe this 400 milliseconds could mean a big meaningful difference, because with milliseconds you can either bump another car or you can avoid bumping a car. So if it was those kind of application, this difference could be meaningful. But if it was about gaming, then maybe 400 milliseconds of difference, even though it's statistically significant, it could be nothing or not that meaningful. So again, together with the significance level, which is probability of showing that if there is a significant difference between the two conditions, you will still have to consider the amount of difference between the two conditions and see if that's a meaningful difference or not, depending on the application. And another thing that you will have to avoid when you're writing your report is no significant, if you find no significant difference between the conditions, even if you don't find significant difference between the conditions, you cannot really say that the conditions are the same. So this is another thing that there are different statistical methods that if you want to prove the two things are the same, there is other methods in statistical field that's called equivalent testing. But most of the statistical tests we use in HCI always is focused on if you're making a statistical significant difference between the two or not. And finding no significant difference between the two not only means that the two are equivalent. So you cannot say, since there was no significant difference found, this and this is the same. You cannot really say that. It's all about just the conclusion. We cannot really say these two are different. So to do some activity, maybe we can think of some hypotheses, examples of hypotheses for our studies, like robot you're working on App, right? Use the app. So can you think of some sort of measurements you want to measure when you are testing your app? Like, let's say you have your old version of app and you came up with a new version of app.
I guess reaction time, task completion time. Like
Test completion time. So test completion time would be the measurement, and maybe the interface could be the dependent variable. And if we formulate the hypothesis,
signal would be.
It's easier if you do the alternative hypothesis first because that's what you want to really claim. So.
But the new interface is faster to use than the old one.
Yeah. So that will be the alternative hypothesis. So with the new interface, users will complete the task faster than the older one, and then the null hypothesis will be the other way around, which is there will be no difference between the new interface and the old interface in terms of task completion time. Would you like to give an examples of yours?
The one would be the task completion time.
Okay.
And the other one would be the stress on the operator.
Stress on operator, yeah.
The new interface will assist the operators to reach the goal. And there is no much stress and confusion.
Mm. So maybe you can make in a sentence, try to make that in a sentence as an alternative hypothesis.
This interface reduce the task completion time and reduce the stress with the operator.
Mm. Mm.
And the null would be, there won't be any difference.
Yeah, there will be no difference. And yeah, so that was a good way to show your hypothesis. One thing you might have to be careful is, again, you can have a high-level hypothesis, and then you can break down into individual hypotheses. But it's always important when the lowest level hypothesis that you test using the statistical test, it might be better if you separate them into one measurements. So if it was test completion time and stress level, then maybe it's better to have two hypotheses, one saying about test completion time and one saying about stress level. So that because when you run a statistical test, it's all about going the hypothesis one by one, and it's more formal if you have them in a separate sentences or separate hypotheses. Okay, all right. Melody, it's very early stage of your of your thesis research, I understand, but you can think of something around insurance.
No, in terms of the virtual agency.
Virtual agents, yeah.
That the working efficiency is the same with the real agency.
So you can compare the efficiency test, the efficiency of doing the insurance claim between the virtual agents and the real agents. And then could you put them into a sentence for an alternative hypothesis? Okay, so could be something like there is with the virtual agents, people can make the claiming experience more efficient than when dealing with the real agents, or something like that could be an alternate hypothesis. And the null hypothesis would be there will be no difference between the virtual agent and the real agent in terms of completing the test, insurance claim or something could be one way of doing the hypothesis. Okay, Joshua?
I think the dependent variable would be the sense of presence.
Sense of presence?
And body in the virtual world,
Mm.
and it varies if you can see it. So the alternative hypothesis would be there will be an increased sense of presence, or there's no sense of presence is the same,
Mm.
and the null will be decrease of sense of presence.
Mm. Okay. So you've said something about no difference or decreasing or increasing type of thing, right? One thing I would like to add, I think that was a good example because that kind of gives you a chance to a little bit clarify how to formulate the hypothesis. You can certainly make that kind of hypothesis saying that the new interface would be better or at least same as the traditional one, but not worse. So it's certainly valid. But the problem is we'll learn about statistical tools in the next lecture. But in most of the cases, the statistical tool available that we can use is focused on testing if there is a difference or not. In many cases, it doesn't tell us which one is higher or less, but it's all about if there is a difference or not. So since those are the statistical tools that are available we can use, it's more easier or more clear if we formulate the hypothesis in that way as well. So thinking of that statistical tool available, if we reformulate your hypothesis, it will become the alternative hypothesis will become there will be a difference in sense of presence level when comparing, depending on either they see or not see their body in the virtual environment. That will be the alternative hypothesis, because all you want to do is to prove that seeing your body makes a better experience, right? And the null hypothesis will be there is no difference of sense of presence, between seeing or not seeing the body in the virtual environment. So unfortunately, the statistical test doesn't say about which one is higher or which one is lesser with the probability of the statistical test. But you can say once you have the conclusion either rejecting or supporting the hypothesis, say that there was a significant difference between the two, what you can actually go back to is the descriptive statistics. So for example, here, the statistical tool we used here, for example, is a t-test, and it printed out the p-value of 0.04, so we can say there is a significant difference. All it says is there is a difference between the two, but it doesn't say which one is faster or slower. But if we go back to this descriptive statistics, which is an average test completion time, we can definitely say, since there is a difference between the two, this one is taking more time than the other one. So by using other statistics, you can actually make a conclusion that this is faster than the other, or this is slower than the other. But with the inferential statistics, which is printing out the p-value, we cannot really say which one is faster or which one is slower. But with the descriptive statistics, which we learned at the last lecture, we can add those information into it. So that's about the hypothesis testing. And next will be the experimental design. But maybe I think it might be better to stop here. It's almost 11:30 now. So we'll stop here, and we'll continue on with the rest of the slides, which will cover about in details how we're going to design the experiment and more tips of how you run the study and so forth. So we'll stop here today. Any questions so far? It's a little bit could be a little bit confusing at the first time, but you'll get more used to it once you start practicing with your own projects. So in essence, first of all, define your hypothesis, what you really want to say, negate it to make a null hypothesis, and then run a statistical test. The test will tell you either you can reject H0 or not. So if the p-value is lower than 0.5, then you can reject H0 so that you can support what you really wanted to say, which is the alternative hypothesis. Okay, if you don't have any questions, then maybe we'll dismiss for today's class.